Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're going to go ahead and get started. My name is Mike Ziskowski. I work in Microsoft Research, the Outreach Engineering team, and had the fortune of having Joe DeGaulle be my intern this summer. Joe is a third-year PhD student at University of Illinois, Champaign-Urbana. Did I get that right? I always mix those two up. It's currently advised by Dr. Derek Hoym and Tim Brettel. And his primary interests are in computer vision and robotics, particularly computer vision techniques for quadrotor flight, primarily around applications to problems such as construction site monitoring and civil engineering project inspections. He's a NCAA Division III soccer player, enjoys running and biking. This is Joe's first internship with MSR, but his 6th overall. And he's going to talk today about semi-autonomous quadrotor indoor flight.
Thank you. Hi, thanks for coming. So yeah, as Mike said, my project is titled Towards a System for Safe Indoor Semi-Autonomous Flight. And I worked with Sudipta, sitting out there, and Mike this summer. Okay, yes. Okay, so first, why would anybody want to work on quadrotor-related projects? So the first thing is that there are a lot of applications for which you can apply quadrotors to. So I've listed a few of them here across the top. So monitoring surveillance, that, as Mike mentioned in my intro, can be applied to construction site monitoring. And then you've got things like search and rescue, so sending a quadrotor into a building and trying to find somebody that, without the people going in. You've got inspection tasks, so this is like bridge and tunnels, buildings. This is also kind of in line with my own interests as well. And lastly, consumer products. So I'm sure you're all familiar with several different consumer products that are drone related. So beyond that, maybe why Microsoft or other companies would be interested in doing quadrotor things is because the technology's coming either way, right? So I've got some examples here. Amazon Prime, I'm sure everybody's familiar with their drone delivery project. The next one here is DJI, which is probably the most popular platform for taking handheld video. The third one is the Project Tango, Google's Project Tango, which has been used. So a few of these are links, and I'll show you some videos as long as I have internet. So this Project Tango has actually been used to control a quadrotor. So I have a video, I can demonstrate that. The fourth one is actually acrobatic removers with a quadrotor. So one of the things that might be a common misconception is that quadrotor control and everything has been solved, right? You've seen quadrotors fly through tight spaces and everything, particularly with the pen grasp stuff and the ETH Zurich stuff. But the one thing to know is that a lot of that acrobatic maneuver stuff was done with a motion capture system. So, yeah, so there's a big challenge in getting rid of the motion capture system, which provides you with really good state information. And then lastly is kind of like what I'm considering amongst the state-of-the-art in SLAM technologies, or mapping and localization. So let's see if I have internet. All right, cool. So as I was saying, so this is, that's Project Tango there, the white phone thing, and it's being used to map this environment and provide localization for control in this room. And so they're just flying it around in a set trajectory and demonstrating Project Tango as capable technology for quadrotor control. The only other thing to note about this is that they are still using the inertial measurement unit that's on board the quadrotor as well. So it's just the IMU and Project Tango. Okay, well, I won't belay the issue. I think you get the point. Okay, so the other main one that I wanted to show then is kind of the state-of-the-art in SLAM. So this is LSD SLAM, which was just recently published in ECCV. So what you're seeing here is the actual image and then their color-coded depth map, and then the mapping and localization step taking place in the environment on the right, where the red thing is the camera and the blue is the past cameras with the trajectory. Okay, I'll stop it there. But so you can see that, I don't know how familiar you are with SLAM research, but it's come a long way, I would say. And this is running in real time at like 30 hertz as opposed to a 1 hertz SLAM system. Okay, the other thing then that I wanted to point out, particularly perhaps for drone research here at Microsoft.
So that's SLAM. The processing is done offline, right, or is it on drone?
No, so they do that offline on a ground station, yeah.
So first just collect the data and then
exactly.
ad hoc, post hoc.
Right, yeah. Okay, so, whoops. So the one other thing that I wanted to point out as far as Microsoft is concerned is that there's unique technology here that could be leveraged for drone research that is just kind of like waiting to be used. Of course, the Kinect sensors provide depth and RGB, which is kind of like on the newer end of things. Okay, so the next thing that I wanted to, I guess, talk about here is that I picked these four applications for a reason. One thing, or the two reasons are, one, they could be indoor or GPS denied environments, like going into buildings, going underneath tunnels, etc., are all potentially GPS denied environments. The second thing is that while you could imagine, for example, inspecting a bridge by having a guy stand there and collect data with a quadrotor, he could benefit from having autonomy involved. I think that similarly applies to all four of these applications, and that's why I chose them as opposed to just collecting video for, yourself, selfies or something. Okay.
Just having fewer crashes would be nice too, eh?
Yeah, for sure. So having said that then, the problem statement for this project was, it was twofold, but the first thing was, can we build a safe indoor semi-autonomous like flight system? For example, flying a quadrotor through a living room without it crashing into the walls, grandmother's china, and anyone else that might be walking through the scene. Kind of the other thing that a lot of this has behind it is that what we're really trying to do is also design a system that enables UAV research here at MSR. So a lot of the things that I'll be talking about more broadly apply to that goal as well. Okay, so then the next question is, what do I mean by semi-autonomous? So this is one example of a kind of basic high-level autonomous system that maybe you could design. So we've got the hardware layer here with sensors and actuators. The sensors provide data to the state estimator. Can you see that? I think it's dying. Well, whatever. So the sensors provide data for a state estimate, which then gets passed on to a path planner, which is going to take the current state and get a target state, or where you want to go. And so you pass the current state and the target state to the control block, which then controls your device to go from point A to point B. So then the question is, how does the user fit into this so that you have semi-autonomy? So then you can imagine having user input go into the path planning component. So then the user provides the desired position, or I said desired state, desired position in this case. Okay. So what are some of the challenges of achieving this? So the first thing is ensuring safety. As I mentioned earlier, that can be anything from the safety of the house or the obstacles in the room to the safety of people. Obviously, you don't want to get hit by blades spinning. So that's one challenge. An additional challenge, this is something that I brought up in the related work, is just localization and mapping is not a solved problem for GPS-denied environments. So being able to understand the room that you're in, particularly with dynamic objects, and then figure out where you're at in that room. Along those same lines then is obstacle avoidance. So once you see that there's something in the room, can you plan a path to avoid it? So this is also a topic of research, particularly in the robotics community, is path planning, obstacle avoidance. Okay, so then another thing that is problematic or challenging is that there's a trade-off between the size and the size dimensions of the quadrotor, the way it's built, and its payload capacity and/or the things that you can carry on board. So for example, here I've got LiDAR and Kinect, computer and batteries as examples of things that you need to be able to carry on board the quadrotor. The other thing is that with a bigger quadrotor, it requires more power, which means you have to have a bigger battery. So there's some sort of diminishing returns on making it bigger with a bigger battery. And then lastly, this robotic system is kind of inherently multidisciplinary. So you've got control theory, you've got robotics and path planning, you've got computer vision, aerospace engineering. Even when you get down to trying to debug Windows on your mastermind board, you've got electrical engineering as well. So it's just inherently a multidisciplinary problem, which can make it challenging to keep everything progressing forward. Okay, so what platform did we choose for this problem? As you may have noticed right here, this is the Ascending Technologies Firefly. So just a few things worth mentioning about the Firefly. It has a microcontroller, flight controller on board. So that's where, well, it came on there, and so with that, it works out of the box. So we have flown it manually outside several times, make sure everything's working properly. It's also got GPS, so we flew it using the GPS. I'm sure some of you have flown other ones with GPS, so it works very similar to a DJI, for example. It's also got an inertial measurement unit, or an IMU, which provides accelerations in X, Y, and Z, and velocities in roll, pitch, and yaw. And finally, it has a 500-gram payload, which is more than enough to carry a Kinect, a battery, and the mastermind board. So Kinect, mastermind board. So then, yeah, the next thing is we have a mastermind board on it. So it's a proprietary board developed by Ascending Technologies that has an Intel Core i7 processor on it. Yeah, I mean, it's got whatever, USB ports, FireWire ports, serial ports, etc., so you can connect any sort of device that you want to it for interfacing. It's got Wi-Fi and it's got VGA out, which is nice because you can plug a monitor into this board and then work right on it. And then the last thing is that we chose to use the Microsoft Xbox 360 Kinect. It's light, it can be stripped down and then mounted to the Firefly. So, and it provides both a depth and an RGB image that we registered on top of each other. So Okay. So one other thing then, I spent a long time this summer working on a robot simulator that, I mean, it's for the Firefly. It can also be used for any other sort of robot that you would want to add to this system. So the first thing then, I guess, is so why simulate? So the first thing is it provides easy testing and validation of your algorithms, so control algorithms, vision algorithms, etc. The next thing is that it protects the expensive hardware. So you don't really want to design a new controller and then just put it on it and hit go and see what happens. So having a simulator allows you to test your theories first before you try them on real hardware. The other thing then is that it serves as a blueprint for final implementation. So basically, with the simulator that I have working, you can just essentially port it MATLAB to C, and then you should be able to go. There's, of course, a few caveats to that, but some of that stuff has already been taken care of in terms of like visual odometry stuff, which I'll talk about later. In terms of the actual simulator that I have, so that's a picture of it, and I'll show a demo of it later. Just a few key points, I guess. So I mentioned this earlier, extensibility model for robots, sensors, and obstacles. So the way I made this was with hopes that it can be used with things besides just the quadrotor. So all that you really need to do is create, just follow my template, and you need to implement 4 functions and just add it to the engine and it will run. So this is a control, a draw, and 2 other ones, a physics function, physics, control, draw, and 1 other one, and then it'll just work. And that goes, I have a same sort of idea for sensors and obstacles as well. So you can add cameras, which I have a camera and an IMU in the simulator, which you'll see. And it's extendable. Yeah, so then the other thing is that it simulates the physics, control, sensor readings, obstacles, and noise. Okay, so back to this. The next thing is, how do we take this basic high-level diagram and apply it to the hardware that I just introduced to you, the Firefly's microcontroller and the mastermind board. So let's start by adding in the microcontroller and the mastermind board. Yeah?
How much of this does the simulator simulate? That whole diagram? Or
yeah, everything except for the visual odometry part.
And can you plug in external inputs to your simulator?
Like a real camera, you mean?
Or you know, carry the quadrocopter around and take that input to the...
So not in a raw form. So what I did, because we were interested in this, is you can load point cloud data in, and then that becomes your environment, and then you're flying around in basically a mapped room. In terms of, so it doesn't interface directly with, like, I can't plug a Kinect in here and do this and see it in real time. We actually had a problem with that there's a reason why we didn't do that, which I don't know if you remember why. I don't remember what it is off the top of my head. Because I was trying to do it, remember? And then we had a discussion and decided that it wasn't feasible.
That's okay. I'm just curious.
Yeah.
Thanks.
Okay, so anyway, with the microcontroller and the mastermind board in place, so then the next thing is that we want to take the sensor layer, the hardware layer, sensors and the actuators, and change it into the IMU, the Kinect, and the motors. So if you notice as well then, so as I mentioned earlier, the IMU provides acceleration and velocity data, the Kinect is providing registered RGBD images, and the motors are expecting to receive torques and thrusts, which we'll get to later as well, so don't worry too much about understanding all the inputs and outputs. Okay, so the next thing is we want to take the, we're going to replace the path planner part. So the first thing that we're doing here is that we're taking the user input, which is remote control commands, and we're going to filter that user input into what we're going to call desired position, or where the person wants the quadrotor to go. That's going to enter the path planner, which will be running on the mastermind board. And in addition, the path planner will be receiving the point cloud data because it needs to be able to avoid obstacles. It will be receiving an estimated state, so where the quadrotor thinks it's at currently, and then it will be outputting a target position. So the difference between the desired position and the target position is, so the desired position is where the user wants it to go, but what if the user controls it to go too close to the wall? Then the path planner will push it back away from the wall to protect it. So then that will be the target position that the controller will use. Okay, so then the next part is that we want to take the Kinect data and provide an estimated pose, which we can use for our state estimate. So the first thing here is that you'll see the Kinect 360 RGB image is going into the RGBD visual odometry component. That's going to output an estimate of pose, or 6-degree of freedom pose, so roll, pitch, yaw, XYZ, to an extended Kalman filter. Then the extended Kalman filter is used as a method of data fusion. So using the extended Kalman filter, we can estimate the state, even though the IMU and the odometry are providing data at different rates. Okay, and then lastly, the estimated state goes up and into control. Okay, so the final block then is the control block. In the control block, we're going to be taking the target position that we got from the path planner and our estimated state, and we're going to use a series of 2 loops, an attitude loop and a position control loop and an attitude control loop, in order to go from target position and estimated state to torques and thrusts for the motors. Okay, so now I'm going to go through each component in more detail. We're going to dig down into each component one at a time. So the first one that I'm going to talk about is the RGBD visual odometry. So again, what's happening here is we're passing in registered RGBD images and we're outputting estimated pose. Okay, so this is the method that we used. So we started with a 2D feature tracker, and specifically we were using Harris corners with brief descriptors. So basically what's happening is, so if you look at the image there on the right, those are examples of key points. The red dots are key points in the image. And then if we start progressing forward in time and you're looking at more frames, the blue lines are us tracking those key points from frame to frame. So then using the key points, we're using a method, so it's a 3-point algorithm inside of a ransack loop. So ransack is random sample consensus. Basically what you do is you take the minimum number of points that you need to solve a model, and then you see how many other points you have fit that model, and those become your inliers. And then you sample the minimum number of points again, and you do this iteratively, and then you keep whichever model had the most inliers. So this diagram here, so this is the camera center, the gray box is the image plane, and then it's important to note that, as I mentioned, we do have RGBD images, so we also have the 3D locations of these points. So we have a correspondence between like lowercase a, the image, the feature point, and uppercase A, the 3D point. So then using basically law of cosines, you can triangulate your camera's pose from the 3 points. The 4th point is to solve an ambiguity. So using only 3 points, you end up with 4 solutions, and you can solve specifically for 1 using the 4th point. Okay, so then after you've run ransack and found the estimated camera pose, there's a nonlinear camera pose refinement step that basically takes the camera's pose and all the inliers that matched it and solves the least squares problem to refine the pose. Okay, so I have a demonstration of how this actually works. So let's see. Okay, so before I start it, what you're seeing on the left is going to be an image sequence where we're tracking the feature points in 2D, and then what you're seeing on the right is the camera in a 3D space. So you'll see the trajectory of the camera match what you would expect based on what you're seeing in the 2D image. Yeah. So the points that you're seeing that are red are when they first start being tracked, and then they gradually turn blue as they're tracked longer. But you can see here that we're moving forward, backwards, and then right, left with some rotation.
One thing to add quickly is that there's a notion for keyframe.
Oh, yeah.
And so the system always keeps one old keyframe and keeps forgetting. So
Right.
basically this pipeline can run forever. Its running cost is fixed.
Yes. Yeah, that's a good point. That's also why you see the point cloud data in the world flash, because when it switches keyframes, then it changes the points, because the points differ per keyframe.
Did you think about using the depth maps as well?
I am using the depth maps. So the 3-point algorithm uses the 2D, so let's see.
So you're not triangulating from the 2D images, but actually using the depth data.
Right, well, so what this image here is supposed to represent is the 3-point absolute pose solver, where you've got so like lowercase a, b, and c, for example, are key points in the image. And then uppercase A, B, and C are their corresponding points in 3D, in 3D world.
From the depth map,
Yeah.
right? I thought they were triangulated.
Yeah, well, so there are other ways of doing pose estimation where you only use 2D images, for example. Since we had the Kinect, we chose this method because it makes sense for having the depth data. So the only other thing that I wanted to mention here, so I added this to the slide because for us, we weren't necessarily trying to compete with the state of the art as much as get a working system. So the relative pose error on some various data sets was a way of us verifying that we indeed had a system that was working. So I didn't want to focus too much on that, just state that our intentions. Okay, so the next thing then is, if you remember, we just left the RGBD visual odometry step, and we're passing the estimated pose now into the extended Kalman filter. And similarly, we're passing the IMU readings into the extended Kalman filter. And what we're hoping to get out is an estimate of state. So as I mentioned earlier, the idea behind a Kalman filter is that we're fusing sensor measurements into a state estimate. So this diagram is supposed to represent how this works. So the first thing is you have your current state, which is represented as a Gaussian with a mean and a variance. So x of t minus 1 is your current state, where x is the mean, and p of t minus 1 is your variance. So then using the dynamic model that you have for whatever your robot, you can predict the next state. So for example, let's say that you knew you were applying a velocity forward, you would predict your next state to be some amount forward because you're applying a velocity. So that's what you're seeing with predicted state. That's your mean at your next state given your previous state. And similarly, your variance at your next state given your previous state. Kind of also, somewhat independently then, you have measurements coming in. So a measurement also has a mean and a variance related to it. So that's what you're seeing, the YT and the QT. That's YT being your mean and QT being your variance. So the final sort of step then is that you need to compare what you predicted against what you measured. And by comparing them, you end up with a new estimated state, which you hope, if your sensors are working properly, will be closer to what you want. So in our case, we're estimating roll pitch yaw, XYZ, DX, DY, DZ, D roll, D pitch, and D yaw. And it can even get more involved than that. But
so measurements is the new pose information plus the sensors on board?
Yeah, well, so
how do you rectify it? You know, what if there's a conflict there? The pose says it's over here, but your sensor says it was rolling this way.
Well, so I mean, they can come in at different frame rates. So your IMU, for example, can operate at 1,000 hertz, and then your pose estimates can be at, let's say, 20 hertz. But then you have a model for your measurement, or for each sensor, on how, so its variance, how likely it is to be correct. I mean, if you don't model that stuff properly, then having conflicting values could make your state incorrect. If you model that variance the right way, then you can overcome bad measurements. That's kind of the whole idea.
The system still needs like checks for gross errors, because this is only modeling Gaussian errors. So gross errors will still have to be caught using heuristics or other checks removed.
Yeah, there's also other methods of fusing data too, like particle filter, for example.
I'm trying to figure out which one is using sensors and which one is using the pose information.
Oh, so these are both using sensors, pose and sensors here. This is the previous estimate, and then you predict it by knowing your control inputs. So we know that we had all 4 motors thrusting upward, so we expect Z to be up some amount from our current state. Then we have readings coming in from our sensors that tell us we moved up by some amount, and then you fuse them together to get your final estimate. Yeah.
Go ahead.
Can there be a gap in measurements? Can you be disconnected from the IMU in some sense, and signal drops and then comes back?
Yeah, it's just that. So if so your Gaussian, your covariance will just grow, right? You become more and more uncertain about your actual position, essentially. You need the measurements here in order to regain certainty.
Okay.
If that makes any sense. So if you know that you're at x equals 1, y equals 1, z equals 1, because your pose is telling you that and you're applying control inputs that tell you that, then suddenly your pose is gone. So your variance on, well, I think I'm at 1, 1, 1, but I'm getting less and less sure every time I iterate, because my pose isn't telling me anything about it anymore.
How do you deal with the different sampling rates for the 2 channels, like IMU and are they coming at the same frequency? Are you forcing them to sort of? Or?
They're not. So like I was saying, IMU normally will give you data at, let's say a lower bound of 500 hertz.
And your visual odometry is definitely not that fast.
Yeah, no, it's 20
so you
hertz.
interpolate? Do you interpolate? What do you do?
So there's actually different methods to do it. I have a PDF on how to do this, but I'm not qualified to give you a 100% accurate answer. I haven't completed this part 100% yet.
Okay. So actually related to Ashish's question, what about synchronizing the various devices? So, you're getting measurements from the visual odometry at some frame rate, but also can you trust the timestamps coming off? Like, how do you synchronize temporally all the sensors?
That's actually a hard problem in itself. There's research that goes into doing sensor synchronization.
Assuming synchronized.
Yeah,
timestamps are reliable, and the microcontroller as well as the mastermind. There is some Aztec specific stuff, right, that allows you to do that, right?
Yeah.
Ultimately, I assume you just want to get the latency down as low as possible, right?
Yeah.
Because you probably aren't getting like the sync signal from the rolling shutter of the depth camera.
No. Right.
The timestamp is that's
yeah. So as he said, yeah, we kind of like hope that our model and our system is robust enough to handle the Or
you measure the latency once and factor that in.
Yeah.
Is that what you do? Or?
But it could vary.
It could vary. I don't know. Does it vary?
Yeah, depending on. Is the camera? Is it auto exposure or?
The Kinect?
Can the exposure time of the camera change?
So I think it's a fixed exposure. So what we have it where we grab a frame every time we need one, and it takes long enough when for the tracking and odometry to happen that we grab frames slower than the max frame rate that the Kinect can achieve. So
the IMU typically gives very robust information, but it drifts over time. And so the theory anyway is that the visual odometry will, used with that, will correct that drift error. And you know, the synchronization is a great point, right? That's a uncertainty that we're not sure about yet. This work actually didn't quite get finished.
And then I guess also related to that, the IMU is giving you integrated measurements across multiple sensors individually. So there's a compass, there's a magnetometer, there's accelerometers. Do you trust certain sensors more than others? Because the translation is
the compass.
Not as reliable
the compass is not normally a reliable sensor.
Yeah.
It's mostly just the gyroscope and the accelerometers.
And orientation tends to be better than translation.
Yeah. Yeah, that's why you can use it for attitude control, and that's actually, it works really well for just doing attitude control. The problem is that it will drift, and so the idea was to use the visual odometry to correct the drift, as Mike said.
I mean, if you collect some data, you might be able to run some machine learning to learn the parameters cues for each, and for the unreliables, you know, sensors will have very high Q.
Yeah.
And that'll automatically take care of some of the issues. So.
That's the idea behind using this.
Yeah.
Okay. So then the next thing that I'm going to do is, so we're switching, because we want to make sure we talk about each line that's going to go into the path planner. So now we're going to go up top to the user input and filtering the user input. So at this point, what we're doing is the user is saying that they want it to thrust upward or they want it to pitch forward, and we want to filter that into what we're going to call our desired position. So we took kind of a, a conservative approach here, because we only have one camera on the device. So we don't really know what's behind us, and we didn't want to rely on computational power required for doing a full-blown SLAM environment, as well as that still doesn't help you with moving obstacles. So what we decided to do basically was limit it so that it can only move in the direction it can guarantee there's nothing in its way. So what you're seeing here is, so I don't know if you're familiar with how to fly a quadrotor, but basically this is an example of a remote control you might have. So you've got two sticks, the left and the right. So this represents what happens if you push up, down, left, or right. So you increase thrust, decrease thrust, yaw counterclockwise and clockwise on the left stick. And so on the right stick then, if you push up, you pitch forward. If you push back, you pitch back. If you go left, you roll left. And if you go right, you roll right. So what we want to do then, based on our goal of only moving in the direction where you can see, we wanted to remove rolling and moving backwards. So that's why those three options are red. So the ones in green are the ones that we're leaving enabled. The one thing is, you can imagine that you could thrust into the ceiling or into the ground. Kind of like a future work thing would be to put a sonar sensor or something, just so that you can, it doesn't need to be that precise, you just need to know ceiling and ground. So, but in the meantime, we do not have any sonar sensors or infrared sensors on the Firefly. Okay, so moving right along then. After we filtered it, we know that so if the user presses forward, pitch forward, what we're doing is we're creating some desired position that's like some virtual position in front of where you're currently oriented. So for the path planner, we're taking in the registered RGBD image, or what we really care about is the point cloud, which is a small map of the environment that we're looking at. The desired position coming from the last step, the estimated state coming from the Kalman filter, and what we want to do is output a target position. Yes.
Wouldn't you want to allow backward thrust to slow down forward momentum? So in other words, instead of turning off the control inputs, wouldn't you want to turn off desired position can't go backwards, not your control? Yeah,
so that's true. And something that we have talked about, it's true, that's basically our intention. The reason that it's not something that I guess, emphasize is that the quadrotor moves very slowly. So the model that we have assumes, and it's a standard model you'll find in the ETH Zurich and Penn papers, but it assumes that you're in almost stationary. You're almost stationary in motion. So when if you pitch too far, then you break the model, and the model won't keep you in a stable state. So by basically saying that we move really slowly, I'm assuming that you're like infinitesimally in front of your desired position is infinitesimally in front of your current position, and that you don't care about going backwards that much.
The thing, at least in a simulation, if you center the control, you're going slow enough that your desired position will be current.
The velocity momentum isn't high enough for it to. If you just stop pressing it, it basically just immediately stops.
Well, air has like very little friction, so it still flies like a boat even if it's going slowly.
Well, yeah. So it's something that we have to extend on in the future, but yeah. Okay. So the path planning step then. So the diagram here. So this is current position here in blue. That's that white part you can imagine as a camera frustum. And the white dots are the point cloud. So the sort of like first naive method that we tried just to get something up and running is that we basically model the point cloud as a wall with a center point, which I'm just taking the mean of the points and I'm calling that obs. Okay, so you can see it over there as well. So then the next thing is, let's say that our desired position, so that's green, is somewhere close to the wall. What we do is we find the vector essentially from the mean of the wall to the desired point, and that vector is dq. Okay, then we have some buffer, right? We want to stay some distance away from this wall. So in the picture, that's the yellow dashed line, and the distance, the quantity distance is delta. So if the length of dq is less than our buffer, we know that we're inside of it and we need to do something. So then the last step then is that we push the target position. So we start at the mean position and we normalize the vector to a length of 1, and then we push it out by the distance to put the target out on the buffer in a normal direction to dq, or in the same direction as dq, I mean. Yeah.
Or is it continuous time in your equation?
I mean, on the quadrotor, it's discrete, right?
So how do you match that sampling with observed points you're getting?
Well, so the points are only updated every time there's a keyframe, every time we update a keyframe.
30 frames per second, and then you're sending this at 30 frames per second?
It's more like 20 frames per second, but the points remain the same at whatever rate you're iterating your planning loop or your control loop.
The reason I'm asking that is if you're close to an obstacle, how early do you have to send out the control to have that sense of like, okay, we'll be away?
Sure. So I guess this again comes under the assumption that we're moving slow enough that it's not too much of a problem. Yeah, I don't know how quickly you have to send a signal, but I don't know. I think that it's fast enough. It does run fast enough. Even though it's 20 hertz is how often we update the point cloud, the control loop itself can run faster than 20 hertz, and the point cloud remains the same until a keyframe updates it.
So what you're getting at is the dynamics of the vehicle versus the update rate of the imagery that detects the object.
Because that relates to observed and predicted state as well.
Yep. Mm-hmm. The assumption we made early on in this project was that the dynamics of the vehicle would be limited so that it would only fly as fast as we could ensure the reaction of the vehicle could avoid objects based off the update rate of the imagery itself. So, because I don't think we can control a lot of what happens in the frame rate of the sensor. And as a starting point, I think that makes sense because we're not trying to do really high dynamic maneuvers in an indoor environment. It's really about avoiding obstacles in the sort of first degree of solving the problem. But you're absolutely right. At some point, you have to take into account the dynamics of the vehicle, and it's that's going to the camera or the obstacle avoidance routine is going to limit that until that can no longer be the tempo, then it'll be something else. Probably the vehicle itself is, that microcontroller is really fast, so it probably will be the sensor, as far as I can see.
Were you segmenting the point cloud in some way, or so this was taking the mean across the full point cloud?
Well, it's only what the camera can see.
Yeah. So I apologise, I missed the beginning of the talk.
That's okay.
Was the field of view restricted on the Kinect? Or?
Yeah, I mean it's like 45 degrees, let's say.
Still the full field.
It's the standard field of view.
Yeah.
Okay.
Actually, at the moment.
So you might see objects, far away.
Oh yeah, up to 4 meters.
And it's the standard 70-degree field of view.
Yeah.
So
You might be getting ahead of yourself, but how often do you send the control commands? Like what's the frequency of updating your control? So, so my target position is say 2 meters, right?
Yeah.
If I'm moving at a slow rate, probably it'll take me 10 seconds to go there. What do you do for those 10 seconds? Are you updating your control commands every 10 seconds?
Oh, okay. So let me just go one slide ahead. So I think what you're asking is
The control, really.
so yeah, if your desired point is very far away from your current state and you don't regulate it at all, your quadrotor will want to tilt a lot to fly there very fast. Yeah, so that's the second part of the path planning aspect, which is, very simple, but basically it's just we split it up into really small steps and take one step. Yeah, so with the picture here, you can see we find the vector between our current position and our desired position, and then you scale it by something to make it small, and then you just take a step towards it.
Control commands after every segment.
What's that?
So suppose you broke it down to 10 segments.
Yeah.
Do you reevaluate what commands to be sent every segment?
Yeah, you take just one step and then the whole thing reruns. So the desired position could have changed, and it will alter which direction the next EQ is pointing.
And similarly, if the user set a set point somewhere else, you're going to update it right in the middle, or you're going to first finish that?
No, you update right in the middle. Yeah, so you're always moving in the direction of the desired position as fast as that one iteration goes to update the desired position. There's something else I wanted to say. Oh, yeah, so it might be hard to see a little bit, but I included an extra term here that you could use, which I didn't use. So I don't know if you can see it, but right here it says plus beta, and then it's desired velocity minus current velocity. So you can incorporate the velocity of the desired point as well to kind of improve this. The reason that I didn't do that is because we're already limiting it so you can only move in the forward direction. It doesn't seem necessary to take into account velocity, because we're not going to be able to. So what this would do is this would change the vector so that we would slide to strafe a little bit, and we're not allowing the quadrotor to do that, so there's no point in having it. Okay. So yes, so out of the path planning component comes target position. And the sort of final step then is to take our current estimated state and our target position where we want to go and control the motors to get us there. So the first thing, before I do that, I just have a little bit of background in case people aren't completely familiar with the dynamics of a quadrotor. So the first thing, in control theory, a system like a quadrotor is considered an under-actuated system, which means that there's less actuators than degrees of freedom. So the quadrotor has 6 degrees of freedom, and we have 4 motors. So the way that you achieve the different motions is depicted in these different drawings. So the first one is easy thrust. If you want to move upward, you increase the thrust equally of all 4 motors. You move upward. Similarly, if you want to move downward, you decrease it and you move downward, right, as you fight gravity. So the more interesting cases, so the one other thing I should mention then is the spinning of the rotor causes a moment. So the reason that I have red and green for opposite motors is because the green ones are spinning counterclockwise and the red ones are spinning clockwise, so that the moments induced by the motors will cancel each other out so that you don't constantly rotate. If, for example, all 4 motors were red or they were all spinning clockwise, you would have a moment always yawing you. So by having canceling moments, you don't have that problem. With that in mind, though, if you want, so we'll skip to yaw since I'm already talking about it. If you want to yaw, you just need to increase you want to keep them balanced so that you maintain the same height, but you want to increase the motors that correspond to the way you want to yaw, and then you'll induce a moment that will yaw you. So what you're seeing here is that I increase the red motor speed, which induces a clockwise yaw, and then I'm just depicting it across. Similar. Okay, so then the other thing is pitch and roll. So without sort of loss of generality here, if we want to move forward in this quadrotor's frame, we increase the thrust of this motor so that we pitch forward. So that's what. So it's this action with the motors, and then what happens. So we pitch forward along this axis to this point. Then we're at that rotation, and the motors are all pushing us forward because our down vector does not match gravity, right? There's some component that's pushing us forward. And then once we've reached a certain point, then you apply the inverse motion. So what you see there is this arrow on the third picture is now the big one, so that we correct and basically stop ourselves, and then we've pitched forward and moved forward, basically. So I'm pretty sure most people already know this, so I won't spend more time on it. Okay, so the method for control. So as I mentioned earlier, there are 2 loops for control. There's the position and attitude. So the position control, we take in the target position, so that's your X, Y, Z, and yaw. And you get your estimated state, which among other things will include X, Y, Z, and roll, pitch, and yaw. So then we want to calculate some air. So we're taking our target position minus our estimated position, basically. So that's the E pause there is our air. Then it's not too important what this is these are the equations for a PD control loop. So after you've applied the PD control, what you get back is desired roll, pitch, yaw, and thrust. So if you're wondering why thrust continues all the way down, it's because for thrust, all we care about is the air and Z, right? So we don't need to apply roll, pitch, and yaw to achieve a different Z position. Okay, so then the second part is the attitude control. So in the attitude control, we're looking at our airs and angles. So we have desired roll, pitch, and yaw that we got from the position step. And then we're subtracting the roll, pitch, and yaw from our estimated state to get some air and angle. We're doing another PD control loop to get desired torques. So this is torque that changes roll, torque that torque that changes roll, torque that changes pitch, and torque that changes yaw, which we then feed into our motor dynamics and our motors, and then.
Why are you using the integral component for the PD instead of the ID?
Yeah, so the I component, what the I component does is it fixes a steady state error. So if I'm supposed to walk all the way to the wall and touch it, but PD gets me like 80% there, and so the integral part will push me to the wall. But for a system where a user is controlling it, the user can make up for the steady state error on his own. It's not as important.
Do you think I will induce an oscillation that you don't want?
Well, so I can cause instability, yes.
You don't want that, so it's not the...
Yeah, so it wasn't worth the pain and suffering, I guess, to mess with it at the moment, yeah. Okay, so we've gone through all the aspects of the system. So now I guess I'll run quickly through the simulator and then conclude, because it looks like I'm running out of time. Oh boy, is it gonna fit? Okay. So let's see. I'll put it on manual so that I can control it with this. So I'm going to control it with this guy. So the first thing I'm going to do is just show basically a validation of the control. So this is the quadrotor in the environment. So on the left here, you're seeing the current state. I can change the desired state. So for example, if I change it to -2, so the quadrotor will thrust upward. So while it's doing that, on the right side, I have sensor information. So this is the current state of the sensor. It's on the quadrotor, so it'll match the quadrotor state. And then just some information about the camera. And I don't have the features in the scene yet, but I will eventually. So I'll show that later. And then similarly, there's an IMU. Okay, so pixelated looking on this screen. So let's see. I guess an interesting vantage point of the actual way the control works would be something like this. So you'd expect it to pitch backward as it moves. And you can also see how I'm doing tiny little steps, right? Because it pitches and moves, and then pitches and moves, and then pitches and moves. Oh no, this is purely a control part. I have a separate thing for that, yeah. Yeah, I was just more interested in demonstrating the control first, and then I'll.
Will this demonstrate optical avoidance and not hit the wall?
No, not in manual mode.
Oh. Oh, you're in manual. Okay.
Yeah.
So yeah, I mean that's it, right?
Do you know if the MathCAD code depends on infinite numeric precision?
I don't think it does. If it did, it wouldn't work, right?
Well, no, it would work in MATLAB, but not in C#. If that's
I see what you're saying.
That's what I'm worried about. In the port.
There's one part of well, maybe two. I don't know. You can address them. The components you were dependent on in MATLAB that would need to be addressed.
Yeah, but so in terms of infinite precision, so if you have an error the controller should be robust enough to deal with tiny errors, numerical errors, I would say. So I don't think that should be a problem. So let's see, what was I going to do? Let me just do one thing real quick. for the second one.
How do you verify this? Like, translates to the real world correctly? Is there a way to verify this? That this is how?
I don't think Joe's gotten that far.
So I mean, it's never going to match perfectly.
Not
So
perfectly,
you can
but
add
what's the-
you can add noise. So I have the capability of adding noise. One thing you can do is you can actually, so if you have a motion capture system, for example, you can actually estimate what the noise should be and then add it to the simulator, and then you're actually modeling the noise as well. At the moment, I'm just modeling like white. Basically, you can add white noise.
That's why I was asking if you plug in the real inputs.
Yeah. Okay. Whoops. All right, it moves a lot slower in assisted mode, so I'm going to start increasing the Z. So now there are feature points in the scene. So if I start moving, yeah, if anyone has questions, now's a good time to ask questions.
Just to clarify, actually what slow is the rendering code? That's so...
Yeah, when I start adding
It's
features and
basically
stuff like that,
Scatter point.
Yeah, actually, I was going to ask about performance from another angle, which is it'd be great to have a GPU implementation of your path planning.
well, so I'll discuss kind of some improved path planning ideas that we have. I mean, just briefly, because it's something that I would like to do, but you know, didn't have the time, I guess.
So the thing is, these point clouds, they get updated when you get a new keyframe, right? So the thing is therefore concern that your mean position, the obstacle mean, that's going to sort of jitter around or shift around as you
Yeah.
change. Yeah. So you're probably going to smooth it out.
Yeah.
So actually the mean is just a proxy.
Yeah, it's not a good method really. It's
The
just what we.
presentation was just I would say a placeholder. I mean, you would want somebody want to take like the closest point in the
Right.
point cloud.
Yeah.
That's the most conservative thing.
Right.
Ideally, you would
It
want some
depends.
geometric
It
simplification.
depends if you went to Caltech, then you do the closest point. If you went to some other university, you might do average.
Yeah, but average is bad because you could have a fence and then the point sample of the
Right.
fence would
Yeah.
be invisible to the
Yeah,
environment.
right.
You want that. So
Yeah.
I
I think we should treat it as a random variable. Where
Just very simple segmentation based on
Right.
depth, discontinuity, and then fit planes to
Yeah.
That's
objects.
Yeah. So kind of the reason I didn't want to fit planes to things is it can be expensive.
any of these points where you come up with a single estimate will have this jitter. Like mean is one parameterization,
Yeah.
right? So I think the right way to deal with it is as a random variable, right? Probably.
give it more time
Or
actually.
fuse depth maps.
Right, fuse that map and build a local map that the local meanings like some radius around where
Yeah.
you are.
I mean, the nice thing about this approach is you don't have to deal with any of that global adjustment
Right.
of the map,
Yes.
which is nice. There's no bundle adjustment.
What we wanted to do, and like he was saying, with more time, was have like a history, small history, so you know the last maybe 5 point clouds that you saw, and then come up with a way to have the point clouds themselves influence the desired position, as opposed to fitting planes to things.
Yeah, maybe it's not a major change actually. Maybe you could fuse into the keyframe. So you do 2D fusion into the keyframe with, like 30 or so nearby depth
You
maps.
think of having
Or at
basically
least-
some control points which would then essentially interpolate to get a proxy for the geometry.
Yeah, just so long as you can delete irrelevant history. Because you might have yawed a long way and that history no longer.
So what are we seeing here, Joe? You're seeing the.
Oh yeah. So let me rotate it real quick. So you can see the camera is you can see the points the camera is capturing, and then you can see them rendered on the screen right there. So for example, if I you can see that the sort of jitter of the points induced by the quadrotor pitching forward as I slide forward.
Ever so slightly.
Yeah.
It's a little hard to.
It's just flying super slow,
the
right?
feature
Yeah.
points are on the planes.
Or it's rendering super slow.
Yes.
And they're green. They turn green when the camera can see them, and then they show up over here.
Right. Yeah.
And then, so does this include the part where you're changing the desired position? Taking into account the wall, and now you're not allowing the.
Yeah, but it's
It's gonna take a long time.
it wasn't working right the last time I tried it. I started hacking this apart in the last 2 days, and I screwed something up. That's what I was telling you. I suspect that it will go unstable here.
Did you guys think about like proximity sensors or even cheap laser rangefinders?
So you can put a rangefinder on that.
Yeah.
I mean, even Ascending Technologies sells one, but I think that we wanted to try and use Microsoft's technology.
I think this gives you a lot more flexibility, but on top of, just for an additional sensor.
Yeah. Well, so one of the things I mentioned was having an IR sensor pointing up and down at least, or an infrared sensor, some sort of depth sensor, so at the moment I allow you to thrust up and down, but really you need something there to make sure you don't hit the ceiling or the ground. But you don't need the resolution that a Kinect gives you, assuming that we're in normal rooms.
I think the key to the use of the Kinect was the visual odometry part.
Yeah.
Using with IMU, because knowing where you are is one of the biggest problems. But then the obstacle avoidance piece, having that depth map, basically we allowed us to use that sensor for two different things.
What's your estimate? How fast can you go?
How fast?
With this algorithm, like what's the upper bound?
Like frame rate?
Not frame rate, like speed, the velocity for this. How?
I mean, it would be up to tweaking that alpha parameter. So how?
Ballpark number, like if you got them, like what do you think?
Oh, you mean how fast can I go before it starts to
go crazy? Yeah.
I don't know, a meter per second. That seems really fast. Maybe less than that. I don't know. It's hard for me to say without testing it. Yeah, I mean, I have done experiments using the same model with a motion capture system that was definitely moving at least a half a meter per second, if not a meter per second. But this is sort of different when you have the motion capture is very helpful.
So, and the bottleneck is not the fact that you can do pose estimation all that. The bottleneck is probably the fact that if you go faster, you'll have momentum, so that you might not be fast enough to stop or slow down.
Right. You'll break into that buffer.
Yeah.
That you considered a soft wall, is what we call it.
So it's not the computation, it's not the sensing, it's not maybe it's the controls.
I think the limitation really is how fast you can detect an object.
Really?
I think so.
No, I think it's also related to the backward patrol thing that Chris was talking about.
Yeah, it's
reversing
it, right?
Then you can slow down. If you don't have that, then you're limited to moving slowly because you have to take that momentum.
So it's the controls issue. It's really the controls issue.
Right, but that backwards thing is only a limitation on the user control. If you've detected an object and you're moving so fast that you've actually got your desired positions behind you, that's not being limited by your code, I don't think. So it still could, cause backwards movement. It's just that the user's not allowed to do that because the camera can't see behind it.
Yeah, the control will still move you backwards without a problem.
But I mean, it's all at this, it's a dynamic system. I mean, you really have to put the pieces together and try it.
We'll try it and see what
Really try it, get it on this thing, try it.
I've noticed when I fly my AR drone, as it gets closer to the wall, it's like it changes, and sometimes it gets confused, and and there's no smarts in that. But is there some aerodynamics as it gets closer to an object or close to a wall that you have to take into account?
Yeah, there definitely is.
Okay.
I don't know, Kyon, do you have?
So you mean that if you air drone touch the wall and it flips over to the wall?
It's almost like as it gets closer to the wall, the aerodynamics change a little bit, and it doesn't quite know how to handle it, so it's like sucked into the wall somehow.
It's the prop wash, right? The prop wash is
And that could be, yeah.
Maybe it's influencing
It's
the
influencing across-
sonar sensors or something.
You can install, right?
If it was that or aerodynamics.
For instance, right, your drone near the ground, it's wobbly, right? The same effect.
Yeah.
Or if you get too close to the
The
ceiling.
ceiling, exactly the same
Oh,
thing.
yeah,
So
it's to the ceiling too, I've noticed.
maybe you
Yeah.
can detect that and put that as a signal as well.
Yeah.
Like, a final check.
Yeah, that's actually not bad. Like
Yeah.
once
Because,
you got to some parameter of
Yeah, it's like-
stability, it's like, woo!
yeah, and I'll share a funny example. I brought the AR drone to a group, and they wanted to have it come up out of a box and kind of carry a little banner on the bottom. But the aerodynamics inside the box were like too close to the wall, right? It didn't know how to take off inside the box because the wind was just,
Oh, yeah.
that wasn't, so
Yeah.
there might be something there that you could use.
So that phenomenon is written in the first page in the helicopter dynamics.
Oh, really?
Yeah.
Okay.
So I forgot the terminology of that, but
Okay.
yeah,
Okay.
it's dangerous anyway.
Well, it's the,
Yeah.
the upwash.
So the helicopter pilot should not be in between the building. It has the same
I see. Interesting. Okay.
There was some accident.
Yeah, because the air comes up around,
Air, yeah.
back down through the
Back
top,
down.
and you almost just can't get it.
Okay. All right. Thanks. I wondered what was causing it, and I thought it might be useful as you get close to an object.
Yeah,
Could have
if
the
you
same
could detect an instability.
Sorry, actually.
Okay, so yeah, just very quickly, there are things that still need to be done, obviously. I mean, so porting this simulator stuff to the Firefly is one of the first things. Finishing up the EKF stuff. And then there's some sort of like hardware tweaks that need to be done, like getting the two boards communicating over serial port. So I just got this 2 weeks ago, by the way. So that's part of why that's part of also what motivated the simulator also, because I had to work on it before I actually got the device. And then yeah, the sort of the last thing would be validating the system with test flights. So then the only other thing was, so we already talked about the point cloud driven obstacle avoidance. The one other thing that kind of was a neat problem that we came upon was, so with the RGBD visual odometry, there's this problem where, like, so if you imagine the quadrotor flying in, or the hex rotor flying in the lobby area of 99, and it was up 10 feet and far away from any wall, you would be getting no depth data, which means your odometry would not work. So it was an interesting idea to have a hybrid system that was still able to survive under these sort of conditions, but then once you had depth data, it was able to leverage that as well. So.
Yeah, which was the question that I first had about, are you actually triangulating across the RGB sequence? Because it's actually a lot of the features that are far away that are locking on the six dot phase of the camera, not the close features. So I think that's a really good idea.
Yeah.
So this is the beginning of an internship or midway through an internship?
No, this is the end.
This is the end. Now hopefully part 2 is
Hopefully more will
There's
come.
part 2. Good.
We had well actually,
Great.
so yeah, Sudipta we kind of tag teamed on this one, and then Hayan's just getting going. Hopefully he can do some great stuff. One of the challenges we had, was finding a device that could actually run Windows on something that was small form factor.
Yeah.
And so that's how we basically settled on this
So this thing
unit.
is running Windows?
Yeah, we've got 2 different ones that run Windows now, actually. His uses the bricks.
Right, and we found another one. We've had a lot, we knew hardware was going to be an issue, but we ran into more problems on this than I would imagine. We had to do all sorts of BIOS flashing and serial port manipulation. When we told these guys what we were doing, they never said anything until we finally got the unit. And then when we tried to load Windows, it didn't work. And then like, oh, well, we've never tried to run Windows on this thing. So we were blazing trails the whole way. And then it got stuck in customs for weeks and all sorts of crazy problems.
How does this operator compare to like the Pixel platform in terms of compute?
I mean, it's very similar, right?
Very
The Pixhawk gives you as a flight controller with inputs to it that.
The main difference with the Aztec models is that it comes with this high-level computer, which is what the Mastermind is. It's a Core i7 processor.
Yeah.
The problem is if you're going to build your own, and Jan is an intern working with me who's working on another project where he's actually built an off-the-shelf, he's taken an off-the-shelf quadrotor, attached a computer to it, and figured out how to make it talk to the Pixhawk.
Right.
So we when we started out, we had these 2 platforms we were building. One we knew was something that the UPenn and the ETH groups have validated.
Yeah.
We knew was possible, so that's the Aztec. This is something basically which we have built on the way, and he's got it working. He's made some tweaks to the design.
Okay.
Sort of
that's
platforms.
really interesting.
A lot of time I think was spent on the visual odometry piece up front, and then a lot on the data fusion part. I remember.
I basically spent most of the summer on the odometry and the simulator. In the last 2 weeks, I've worked on getting that SDK compiling and then writing my own code and flashing it on it and getting Windows on it, and so yeah.
Any GPU capability on the device?
So it's got an i7, so it has HD 500 graphics or whatever theoretically, but I've never tried to use that stuff at all. And I mean, it's not technically a GPU, but okay. Yeah, well, so I guess thanks to Mike and Sudipta for helping and mentoring me this summer. Thanks to the outreach group and the interactive media group, and then they're not here, but Patrick Theron and Chris O'Dowd and the rest of the hardware people helped me with getting the Kinect so that it would mount on there, and just I don't know, get power supply so that we could run the Mastermind board without a battery, and then Greg. So Jason Walgamuth and Mike Flora are Windows people. So we had to get in touch with the people over in the Windows group, and Greg sat with me for, I don't know, a week in the room for us to get Windows booting. So thanks to them as well.
All right.